But I want to welcome everyone to the final installment of the AI-SDM seminar series for the semester. We're going with a webinar format today because it's graduation weekend at CMU, and I believe it's catching just the end of finals week at Harvard as well. So we're lucky today to have with us Ariel Procaccia, who is the Gordon McKay Professor of Computer Science at Harvard University. He's also a project leader within one of our foundational thrusts within the collective thrust in AI-SDM. And he's yet another speaker that we're hosting from the Institute with very strong CMU ties. So his talk today will combine a mathematical understanding of voting with an implementation via large language models. So we're really looking forward to your talk. And Ariel, please take it away.
Thanks so much, Norm. Good to see everybody. I know a lot of people here, and I'm hoping to meet some of the others in the Q&A. So the title of the talk is Generative Social Choice. And as you can see, there is some AI-generated art in this talk. It's appropriate for the topic. It can also be a bit spooky, but I think that's a feature as well, because it kind of reminds us of some of the dangers of this technology, and I'll come back to this point later on. So this is a joint work with Sarah, Paul, David, Gili, Itai, and Manuel. Most of us are at Harvard. All of us were at Harvard during this work, but Paul is now joining the Cornell faculty, and Manuel just joined Midjourney, which is a generative AI company. Okay, so I like to motivate this work with kind of thinking about Brexit as an example. So think back to 2016. And one arguable way to think about the dilemma facing British voters at the time is which policy would best address some of the UK's problems. And of course, there were two policies on the table that voters were choosing from in referendum. One was leaving the European Union, and the other was basically doing nothing. But there are many other intermediate policies on the spectrum between these two extremes that could have had a larger degree of support. Right? And more generally, there could be many other policies not even on the spectrum that might even be better. So for example, you can imagine ditching British cuisine for French cuisine, which personally I think would be a pretty good move. You could imagine policy that relocates the royal family to California. You can imagine any number of other arbitrary random policies, some of which might be better solutions to some of the problems that the UK had at the time. So what I want to think about is this kind of open-ended questions where we want to select a policy or a bill, something where there's a very large set of alternatives that we are choosing from. And I want to kind of start from social choice theory, which is this area of math and economics and computer science and political science that thinks about how to aggregate individual preferences or opinions towards collective decisions in a mathematical way. So I want to start from that, but I want to argue that social choice theory is not that well equipped to dealing with these open-ended questions, because typically it deals with a very small predetermined set of alternatives. And I claim that large language models can help us overcome this issue. So there are two particular challenges that we have to overcome, and LLMs help with both. One is this issue of unforeseen alternatives. When we're thinking about the space of all policies, all bills, there are many potential alternatives, policies, for example, that we can't think about in advance. And what large language models allow us to do is to generate new alternatives that, again, could potentially garner more consensus than the ones that were on the table initially, that were predetermined. The other related issue is that typically in social choice and voting, we ask people to express their preferences explicitly over the alternatives. So we can ask them to rank the alternatives, to specify their favorite alternative, and so on. When we have these unforeseen alternatives, this very large space with unforeseen alternatives, we can't ask participants to explicitly express their preferences over all of the alternatives in this space. So what large language models allow us to do is to have people specify their preferences or priorities or values as free-form text. And the LLM can then extrapolate from that input, can predict what this person would have wanted, their degree of satisfaction with some new unforeseen alternative. So that's kind of the very high level idea of how large language models can help address this shortcoming of social choice. The thing is that this combination of social choice and large language models seems pretty odd because social choice, as I mentioned, is a theory that is very mathematical. It deals with mathematical guarantees, whereas large language models are, notoriously impervious to theoretical analysis. So to combine the two things, we're proposing this framework that we call generative social choice. And it basically consists of two steps. So the first step is assuming that we have access to an oracle that can answer certain queries perfectly. So the oracle will be the large language model. And the assumption here is that the large language model can answer some queries perfectly. And under this assumption, we want to give hard theoretical guarantees on the properties of the outcome of our democratic process. The second stage is recognizing that, of course, large language models will not give us perfect answers. So what we want to do here is empirically validate that we can at least get reasonably reliable answers to the types of queries that we need. And one nice thing about this approach is that it's future-proof in the sense that even if now, the answers are not amazing, the answers we can get to the queries, as LLMs rapidly improve, we'll only be getting better and better answers to the types of queries that we need, and the outcome, the results, will only improve as the LLM improves. So this is kind of the very high-level idea behind the approach. Now we've instantiated, by the way, of course, feel free to stop me at any time. You can kind of raise your hand virtually. I'll see this on my screen. So we instantiated this approach in the context of a particular task. And this is the task of generating a slate of statements that reflects the diversity of opinions expressed by participants. This is motivated by a system that's in pretty wide use called Polis, like the Greek city-state. So Polis has been deployed pretty widely around the world. For example, pretty famously in Taiwan as part of the V-Taiwan initiative. It was used on a national level to kind of get people's opinions and synthesize them on a variety of issues. So the way Polis works is that people do two things. One of them is they submit comments on the question at hand. So in this example, I asked GPT-4 to, the question, what is generative social choice? It gave me an example, which I put into Polis as a comment. And then, as you can see, other participants can vote on this comment. So that they have agree or disagree buttons where they basically upvote or downvote the comment. Okay, so overall, you do two things. You submit comments optionally, and you also, the system routes comments made by other people to you, and then you vote to agree or disagree with these comments. And notice that kind of in a large scale deliberation, you might have many thousands of comments. So people would usually only see a small fraction of these comments. Now, what Polis does is it then presents the kind of data to decision makers in various ways in order to distill what the important comments were. So for example, one naive thing here on the left is just kind of looking at the most popular comments, the ones that had a large degree of consensus. On the right, it's an example of a more interesting thing that Polis displays. So it has a method for clustering participants with similar opinions in each cluster. And then it identifies comments that are especially representative of each of the clusters and shows these comments. Right? So by looking at the comments for each cluster that represent the cluster, that gives you a really good idea of the diversity of opinions in the conversation. So this is the kind of thing we want to do with this first implementation of the generative social choice approach. But there are a couple of fundamental differences from Polis. So one difference is around the output, where in Polis, the output will ultimately be a subset of comments submitted by participants. So it's the exact same comments that were submitted by participants. And this is really a shortcoming because many of the comments, like if you look at the data, many of the comments are pretty shallow. Some of them are kind of platitudes, which are kind of comments that don't have a lot of content, but people would usually agree with because there's nothing really to disagree with. So these are often comments that come out of the process and are not very informative in terms of decision making. In the generative social choice approach, for better or worse, the output statements are ones that are generated by a large language model. So the idea is to do it in a way that these comments are meaningful, have content, and wouldn't be platitudes, for example. In terms of guarantees, so Polis, of course, does not try to give theoretical guarantees, whereas in the generative social choice approach, the foundations are processes that give provable representation guarantees under certain assumptions. And finally, in terms of the interaction, Polis requires a dedicated website or app because you both submit comments, but also you have to vote on comments submitted by other people. In the approach I'll tell you about, a pre-designed form is sufficient. Just a survey is sufficient because your opinion is enough to also predict what your opinion would be on new statements, on new comments. So we don't need you to explicitly vote on statements made by other people. Okay, so in a bit more detail and kind of trying to start to understand how this works at a technical level. So the input is going to be survey responses from some number n of participants. The output, as I mentioned, is a provably representative slate of k statements for some number k. And we'll talk about what provably representative means in 10 minutes or so. Now, in the background, there's some algorithm that's running, and of course, taking the input and turning it into the output through a bunch of steps. As building blocks, the algorithm relies on queries to an oracle, where the oracle can be anything, but in our implementation, the oracle will be a large language model. Okay, so there are certain queries that the algorithm asks the oracle, and then there's some loop that's happening, and we'll talk about that loop later, that is kind of iteratively asking these queries, getting answers, and doing stuff based on the answers it's getting. So let me start by kind of talking a bit about what are these mysterious queries that we need to ask the LLM. And that's really the heart of the approach. That's where we're actually using the LLM in order to kind of gain some powerful information. So what are the queries? The first query is a discriminative query, which gets as input a participant represented by their survey response and a textual statement. And the goal is to predict the participant's level of satisfaction or level of happiness or utility for the textual statement, right? So the output is the given participant's level of satisfaction for the given statement. So this is the query that does the prediction step. The other query is a more ambitious query. It's a generative query. The text as input a subset of participants represented by their survey responses again, and an integer r. And the output, so intuitively, what we want is to generate a statement that makes many of the participants happy. Okay, so technically, what we want is a statement that maximizes the R highest level of satisfaction among the members of the given subset. So, to parse this, imagine, if you have some statement, take everybody's level of satisfaction for that statement and sort the participants, the end participants, by their level of satisfaction. And now look in this order at the R highest level of satisfaction. That is kind of what we are measuring for this statement. And what the generative query is doing is generating the statement that maximizes this objective, such that when you sort everybody's satisfaction, the R highest one will be as high as possible. Okay, hopefully this makes sense. Again, please feel free to jump in with questions. Okay, so let's go back to the framework, and now I want to kind of start talking in a bit more detail about how we instantiate each one of these steps. So remember that step one was giving representation guarantees, assuming we have perfect answers to the queries that we just talked about. So let me start by explaining what what this representation guarantee is. And this is the most technical part of the talk. So let's start from a more basic representation guarantee. So this is a guarantee that was introduced in the context of approval-based committee elections by Aziz et al. Vince Konitzer, who is of course at CMU, and the advisor, for example, of Amin, who I see is here, is one of the authors on this paper. So the initial idea in the paper was selecting a committee that is representative of people's approval votes. So I'm going to kind of transform that. It's basically the same definition, but transform a bit to match our setting. So we say that a slate of statements satisfies justified representation if there is no subset of the n participants of size n over k, whose maximum level of satisfaction for the slate is alpha, and they all have satisfaction at least alpha prime greater than alpha for some other statement. Okay, so let's parse this. First of all, so remember that we have n participants and k statements. So what is n over k? N over k is the size of a subset of participants that intuitively deserves a seat at the table, deserves a statement on the slate in terms of their size. Okay, that's the intuition for why we look at subsets of size n over k. They're large enough to deserve one of the k statements on the slate. They're large enough to be represented by one of the k statements. And notice that the guarantee will be for any subset of size n over k. So there are no predetermined groups here. It's for every subset of size n over k. Okay, and now the next part of the definition says the maximum level of satisfaction for the slate is alpha, and then we don't want it to be the case that there is some other statement that they all have at least alpha prime satisfaction for. So the way to think about this is that if you have a subset of participants that is large enough and cohesive, so they can agree on some statement that has a high level of satisfaction for them, that means that they should also have a high level of satisfaction for the slate. Okay, so if they can agree on some alpha prime level of satisfaction, this property requires that their level of satisfaction for the slate will be at least at alpha prime. It can't be some alpha smaller than alpha prime. So again, the intuition is if you have a subset that is large enough and cohesive enough, they should have a high level of representation for the slate, or it's really like at least one of them should have a high level of representation on the slate. We can't ignore all of them. So let me illustrate this through a violation of this property. So what I'm showing here is n equals 8 participants and k equals 4 statements. So we have a slate of 4 shown as kind of these envelopes on the left. And I'm showing you the level of satisfaction of each participant for each statement on a scale of 0 stars to 4 stars. Now, I've marked in blue the maximum level of satisfaction of any participant for any statement on the slate. Okay, it's kind of the maximum in their column. Now, let's look at the coalition that consists of these two voters that are highlighted. Notice that this is a coalition of size n over k, right? Because 8 over 4 is 2, so we have 2 participants, n over k. And here I'm showing a new statement that both participants have a satisfaction of 4 for this statement. And notice that this is a violation of justified representation because their maximum level of satisfaction for the slate is 3 stars. So alpha equals 3 stars. but alpha prime equals 4 stars. Right? So alpha prime is greater than alpha. There's some, statement they agree on, but they're not getting represented to that degree, and therefore this violates the justified representation constraint. Okay, hopefully that makes sense. So this is justified representation. The property that we introduce is a bit stronger. So the one issue with justified representation is that you could have a situation where, for example, almost all voters have very consistent preferences, but you represent all of them with a single statement on the slate, and then you represent very small minorities with the other statements. What we want in this kind of situation, if almost all of the voters agree, have very similar preferences, we would instead want, statements that capture the nuances in the preferences of this very large majority, rather than representing them all with one statement and then capturing esoteric views with the other statements. So this is something that wouldn't happen under justified representation. So to address this issue, we introduce a stronger property that we call balanced justified representation. For those of you who are familiar with justified representation, probably not many of you, there's like a whole hierarchy of different properties, and we can discuss why some of them may not be appropriate, but this one is a new one that we feel is especially appropriate. So there are some subtle differences between this and justified representation that are highlighted in red. So let me just read this. We say that the slate satisfies balanced justified representation if it also comes with a balanced matching such that there is no subset of the n participants of size n over k whose maximum level of satisfaction for their match statements is alpha, and they all have level of satisfaction alpha prime greater than alpha for another statement. Okay, so let's start with what is balanced matching. Balanced matching is a matching between participants and statements in a way that every statement is associated with n over k participants. Okay, so we're matching every statement to many participants. How many? Roughly n over k. Okay, that's a balanced matching. And now, when we look at what's the level of satisfaction of participants for the slate, we're not looking at their maximum level of satisfaction like before. We're looking at the level of satisfaction for the matched statement. So this is something that's easier to violate, right? Because the participants are potentially deriving a lower level of satisfaction for the slate. So it's easier to find another statement that would have a higher level of satisfaction. And therefore, this is a stronger property. Right? This is something that's easier to violate. If we can't violate it, we're getting a stronger property. So let's illustrate what this looks like. So this is the same example as before, but now in blue, I'm showing a balanced matching between the statements and the participants. So notice that every statement, every row, is matched in blue to two of the participants. And now consider this pair of participants. So imagine that there's some other statement such that the participant on the left has 2 stars for, and the one on the right has 3 stars for. Now, notice that this wouldn't violate justified representation because they both have statements on the slate that they have relatively high satisfaction for. But if you look at their matched statement, they both have only 1 star for the matched statement, and then in both cases, their value for this new statement, which is at least 2 stars, is more than the 1 star, than the alpha equals 1 star that they had for their matched statement. Okay, so this is a violation of balanced justified representation. And notice that this solves the problem that I was talking about before, because now if you have a very large coalition of voters, you can't represent them all with a single statement because of the balancedness constraint, right? Like every statement can only represent n over k of the participants. Okay, so again, hopefully all of this made sense. Even if you missed many of the details, really what I'm trying to convey is more like the spirit of what it means to give a representation guarantee, and this is the type of guarantee that we gave. Again, if you missed the details, it's not important for the rest of the talk. Okay, so let's talk about the algorithm. How does the algorithm work? So I'm going to show you the first iteration of the algorithm, and that will give you a sense of how the whole thing works. It's pretty simple. So we start with the input, the free text opinions of our N participants, and we use them as input to a generative query. Specifically, it's a generative query with R equals N over K. So we ask the query, the LLM, to generate a statement that maximizes the level of the N over K highest level of satisfaction for the given participants. So this generates a statement that becomes part of the output slate. Okay, in this example, we have an output slate of size 2. So it's the first out of 2 statements on the output slate. And then we feed the statement as input into N discriminative queries to get the rating, the predicted rating of each of the N participants on the statement that we just generated. This gives us N ratings for each of the N participants. And now we filter out the N over K best represented opinions, the N over K participants that had the highest rating for the generated statement. Now we're left with N minus N over K free text opinions, right? In our example, we had 4, we filtered 2, and we're left with 2 more. And then in the next iteration, we repeat the same thing with the remaining N minus N over K free text opinions. So in the example, we would have only 2 iterations to generate the slate of size 2, but in general, we have K iterations to generate a slate of size K, where every iteration removes N over K of the participants. Okay, so with this, we can now kind of peer into the crystal ball that we had before, and we have a better understanding of what's actually happening on the back end. And now we can, with the kind of background that I gave, we can now state the theorem more formally. So what is the output? The output is a slate of case statements that provably satisfies balanced justified representation. So again, we take as input the survey responses, we run them through the algorithm that we just saw in K iterations, and the output will be a slate of case statements provably satisfying balanced justified representation, assuming we have perfect answers to our generative and discriminative queries. Okay, so just staying one more minute in theory land. So the most of the theory that we did in the paper that I'll talk about very briefly is thinking about the following question. In the process that I described, we might have generative queries that have that are called on a very large number of participants. If we run this with, think about thousands, tens of thousands, whatever, a large number of participants, you could have a very large input to these generative queries. LLMs today have a pretty limited context window. So if you want to give the survey response of each participant, you're limited in terms of how many survey responses you can squeeze into the context window in order to kind of do the prompt that you need. So the question we're asking is, suppose that the LLM context window limits generative queries to T participants. So we're going to denote this restricted query by Tgen. And the question is, how does that affect our results? So, let me just very briefly mention our answers to this question. So some of the answers are kind of negative. First of all, if you allow T that is slightly smaller than N over K, so specifically N over K times 1 minus 1 over K, then it's impossible to guarantee even justified representation, even the easier property, with any number of Tgen and discriminative queries. Because we just cannot do it at all. Now, slightly better news is that if you have a slightly larger T, so if T is N over K rounded up, then it's possible to guarantee the stronger property of BJR, but albeit with an exponential number of queries. Okay, so then the question is the exponential number necessary? And the answer is yes. So, specifically, we're asking, can you do this in polynomial time? The answer to that is no. If you have K that is slightly smaller than N, even guaranteeing the weaker property, JR, requires an exponential number of N over 8 generative queries. So T equals N over 8. So this is a constant fraction of N, pretty large generative queries. Even if you have this large T, you still need an exponential number of queries like that. So the most practical result here is something that I won't get into at all, but it basically, what we then do to address this is we think about the structure of the set of statements and utilities, the space of statements and utilities. We think of it in terms of VC dimension in learning theoretic terms, and then we develop an algorithm that has very good performance in terms of the VC dimension of the space. So this we view as something that is actually practical, and when this becomes an issue, is something that can really address the problem of limited context window. I mean, it's unclear if this will be a long-term problem as well, because these context windows are growing all the time. And it's not clear that in half a year or a year, this would even be an obstacle. Okay, so this is a good point to ask if there are any questions before we talk a bit about the empirical validation. Okay, cool. So let's talk about step 2 of the framework.
Ariel, there's a question from Aditya in chat.
Oh, so my chat window is not open. Let's see. Okay. Yes, right. So Aditya was asking, are we assuming we define the participants' level of satisfaction for a slate is at least as large as the level of satisfaction of any statement on the slate? Exactly. So you're basically, here it's kind of unit demand preferences where you're satisfied by the maximum of your of this on the slate under justified representation. Under balanced justified representation, you're of course getting utility under your matched statement. There's also a lot of the literature is about additive utilities where you're getting kind of the sum of things on the slate, and there's a lot to say about that. Emin?
Hey Ariel, I had a quick question about the the negative result on the short window size from the previous slide.
Yep.
So when it's less than n over k, 1 minus 1 over k, even with exponential number of queries, you're saying we cannot guarantee getting even justified representation.
Any number of queries. The queries are useless.
Okay. Is there can you give some intuition on where that impossibility comes from? That even the case?
Yeah, it's pretty simple. So the idea is that for any subset of size t, we have a statement that only that subset likes, and think even about approval utilities, so like 0, 1 utilities. For any subset of size t, have a statement that only that subset likes and nobody else likes. And there's also a statement that everybody likes. Now, every time you ask me a t generative query, I give you the statement that only that subset likes.
I see.
And now if you take any k statements that I generated, together they're going to satisfy less than n minus n over k participants. So there's going to be a set of unsatisfied n over k participants, and they are cohesive because there is a statement that satisfies everybody, but I never return that statement to you.
Okay, that makes a lot of sense. Thank you so much.
Cool. Okay, great questions. Okay, so let's talk about the empirical validation. So so we worked quite a bit to kind of implement these queries and validate and kind of evaluate how good the implementation is. The implementation is done as prompts to GPT-4. So there's no fine tuning, just prompt engineering. The data that we use for the validation is data that we run as part of that we got as part of a pilot that I'll tell you about in a few minutes. So for the pilot, we had 200 participants. For the data will be based on the first 100. So these are 100 participants that are stratified according to gender, age, and ethnicity from on the U.S. population. So U.S. residents stratified according to these features. And for each one of them, we asked them for a particular question that we'll talk about in a few minutes. We asked them for their opinion. And we also asked them for their to rate 6 example statements. Now, to validate the discriminative query, what we do is we give it as input the participant's free-form opinion and 5 of the 6 example statements. And we ask it to predict the 6th statement. So we hold out one of the statements and ask to predict the participant's known rating for that 6th statement. So what you're seeing here is on the y-axis, this is the real rating of the participant for the statement. And on the x-axis, this is the distribution of the predicted ratings by the LLM, by GPT-4. So if you look at the first row, what it says is when the participant's rating is not at all, the true rating, then 33% of the time GPT-4 predicts not at all, 23% of the time poorly, 20% of the time somewhat. Oh, I should, by the way, say like the scale here is basically the question is to what degree are you represented by the statement? And this is the scale, not at all, poorly, somewhat, mostly, or perfectly. So when the true thing is not at all, we have 33% for not at all, 23% for poorly, 20% somewhat, 13% mostly, and 11% perfectly. And notice that the cells are colored, are shaded with a darker shade, the higher the probability is. So what you ideally want to see is dark shades on the diagonal, because the diagonal is the right predictions. And you can generally see that this is the case, right? The colors are darker on the diagonal and get lighter as you get further away from the diagonal. So this kind of at a glance says that things are, obviously it's not perfect predictions, but they're pretty nicely calibrated. Like you have, there's definitely a strong signal in the input in terms of predicting the output rating. There's also a subtlety that I don't want to get too much into, but we are actually using the GPT-4 base model, which gives us the entire distribution of predicted answers, and we take the expectation of that distribution. And this works really well because really what we want is kind of a higher number, the higher the real rating is. We don't really care what that number is for our guarantees because they're invariant to monotone transformations. So we really need a pretty weak property on the prediction, which is really nicely satisfied by what we're getting. So we really view this as pretty encouraging results. For the generative query, this is a lot trickier and unfortunately less satisfying in terms of the validation. So there are a couple of issues with validating these generative queries. One is that we don't know the participant's true rating, true level of satisfaction for any given statement. So what we actually do is we use our discriminative queries, even in the implementation of the generative query, to predict the participant's level of satisfaction. And we also use our discriminative query in this evaluation. So that's one issue. The bigger issue is that we have no idea what the optimal solution is, because the generative query is trying to generate the best possible statement out of all statements in the world. And of course, we have no idea what the true best statement is, so we can't really compare. So what we do in the evaluation is something less ambitious. We try to see that the way we implement the generative query kind of makes sense. What is the way in which we implement the generative query? We implement it as an ensemble of several different methods. So I don't want to go into the details too much, but let's call them random 5, all, and nearest neighbor. And here in this experiment, as a benchmark, we'll also have another method, which we'll call random 1. And we kind of, for each one of these methods, we run them in different constellations. For each generated statement, we run our discriminative queries to evaluate the rth highest level of satisfaction. And we take the statement that maximizes this objective among all of the different options. So what you're seeing here is over 50 trials for different subsets of our data.
There's a little bit of that.
Sorry, Derek?
Oh, I'm sorry. That was another video that popped up. My apologies.
Sorry. So what we're seeing here is for like 50 trials for different subsets of our data, we are looking at the kind of our objective value for each one of these methods. And what you can see is that when you take the maximum in red on the right, this is better than any of the particular methods. And you can also kind of see what fraction of the time each of the methods is the maximum. So you can see that really each of them plays a role in getting the best result. So what this at least says, at the very least, is that taking an ensemble of methods really is useful in terms of giving better results than any method in isolation. But again, I think that this validation is pretty limited, and this is really the best we can do right now. what's more satisfying, I think, is this pilot that we ran that really gives an end-to-end validation of the whole approach. So this was done as part of an OpenAI program called Democratic Inputs to AI. So OpenAI, we're looking for kind of novel democratic processes to get inputs on questions in AI governance. And so we participated in this program as one of 10 teams. And the specific question we were looking at for the pilot was to what degree should LLMs be personalized to individual users? But it doesn't really matter for the results what the question was. Now, in the pilot, we had two phases. In each one of them, there were 100 people, the generation phase and validation phase. And again, each one of these samples is stratified on gender, age, and ethnicity from the US population. Now, in the generation phase, we take our N equals 100 participants. We give them the survey that I mentioned before. We get N responses. And then we run them through our process to get K equals 5 summary statements. So in the illustration, it's 2, but in the pilot, it's K equals 5. Now, for the validation phase, we take a fresh sample of N equals 100 participants, and we ask them to rate the K summary statements from the generation phase. And now we get K times N ratings for these different statements. Then we compute the optimal balanced matching, trying to maximize overall representation, like the sum of representation scores. And then we look at what's the level of satisfaction of each participant for their matched statement. Okay? And what we want to see is that the people in the validation phase are well represented by the statements we generated in the generation phase. So Koti is asking, could you give an example of statements and opinions that were used? So yeah, I don't have examples off the top of my head. As I said, we gave kind of 6 examples of statements on the topic of to what degree should LLMs be personalized. To what degree should LLMs be personalized? And generally the kind of themes that come up are things like privacy, user control over their data, things like that. So the statements were of that sort, kind of saying various things on these topics. Some of the statements were also kind of generated on purpose so that people would not agree with them, to just give some bad examples as well, and generate some controversy. So that's kind of on a high level. I don't remember off the top of my head what the exact formulation was.
Thank you. That would be in your survey, right?
So that's in the paper, yeah. It's in the appendix of the paper.
In the appendix of the paper. Okay, thanks.
Yeah, sure. Okay, so we want to see that let me also mention one other thing in response to Koti's question. I think what you might worry is that the statements, the example statements are kind of priming participants to give very similar answers. But if you also look at the appendix, we have, we kind of looked at, should we be worried about this priming effect? And it doesn't seem to be the case. It seems like the opinions on the slate are quite different from the statements that we gave as examples. So that's, based on our analysis, not something that should be a concern. Okay, so again, like what we want to see is that the fresh sample, the fresh validation sample feels represented by the slate generated in the generation phase. And I think the results are quite encouraging. So what we see is that 75% of participants said that they were perfectly represented by their matched statement, and 18% say that they are mostly represented by their matched statement, so 93% overall. The other 7%, actually 6 of them are somewhat, but all of the other 7 are kind of outliers, so we looked at their opinions, and it seems like they have kind of minority opinions that would be difficult to capture in the way that we want. So overall, we feel like these are very encouraging results. Now, you might worry that it's pretty easy to get these results. That, for example, everybody is pretty happy with all of the statements, so it doesn't really matter. But it turns out that that's not the case. So this last thing I want to show you is showing the level of satisfaction of each of the groups of size 20 for each of the statements. So group 1 is the one that was matched with statement 1, group 2 is the one that was matched with statement 2, and so on. So on the diagonal, you see the distribution of satisfaction levels for the groups, of the groups for their matched statements. And then the rest are the distribution of satisfaction levels for the other statements. And I think you can pretty immediately see by eyeballing this that there is a much higher level of satisfaction for each group for its matched statement. So there really is a strong preference of people in the group for their matched statement compared to the other statement. So this says that there really is a diversity of opinions, and it really matters how you kind of doing this carefully in order to get good representation. Okay, so let me conclude with a take-home message. So, needless to say, I think generative AI offers new building blocks for constructing new types of democratic processes and potentially contributing to democracy. However, you might worry that these AI democratic processes would be affected by all of the issues that we know and worry about in AI, issues with bias and fairness and transparency and accountability and adversarial attacks and what have you. So this is something that is very much a concern. I'm not saying that this work solves all of these concerns, but I think it does take a small step in the direction of alleviating some of these concerns by starting from these theoretical guarantees and building the approach in a way that satisfies these theoretical guarantees. Again, assuming perfect answers to the queries, but at least it gives you some fundamental guarantee that guides the design process in a way that I think leads to more desirable outcomes and alleviates some of these concerns. But again, this is really a first step, and I think there's a lot more work to be done. And we're also kind of working on a number of directions to make these results even more robust. Okay, that's it. Thank you very much.